All right, today we're going to talk about what happens to a reaction system, a reversible reaction that is at equilibrium, and then that equilibrium gets disturbed or stressed. So there's a principle called Le Chatelier's principle that says that if an equilibrium system is stressed, the system will shift in the direction that essentially gets rid of that stress, relieves the stress. So what do we mean? I keep saying, I've already said the word stress several times. What does it mean? A stress is anything that disturbs equilibrium. Okay. So, for example, if we have our equilibrium system and we've got our concentration of reactants and products that are maybe kind of like this, right? And so we've reached equilibrium where the two lines flatten out. But something happens. So, for example, if we have a change in concentration, that would represent a stress on the equilibrium system. Because if I have, reactant A and this is product B, and if I increase the concentration of B, well, that changes my graph, right? That's going to cause a spike in the amount of B, right? Now, what then happens as a result is going to be what we talk about next, because we've disrupted equilibrium here. In addition to changing concentration, we could also change pressure. So adding or removing pressure from a system, especially if a gas is involved, is going to be a stress. And the other thing we can do is change the temperature. We've already talked about the fact that KEQ is dependent upon temperature. So changing the temperature, you might imagine, would do something to that chemical equilibrium system. So let's go through these one at a time. The first one, changing concentration. I already talked about this. If I increase the concentration of something, so we've got our little hypothetical reaction over here. A plus B yields 2C. It gives you a little delta H, but we're going to ignore that. So we've got our system at equilibrium. And if you look at the graph, they're stressing it in a couple places. I'm going to ignore this time 1 and just imagine that that's nice and smooth and going up to a nice horizontal line. So you can see that C reaches a constant concentration. You can see that B reaches a constant concentration, and you can also see that this is actually A, and then this is B. So they're all at a constant concentration. They're all at equilibrium. Okay. If I increase the concentration of B, and I'm talking about at time equals 3, right down here, you can see a big spike in the concentration of B. What that represents is somebody is taking this reaction system and actually dumping in more of substance B. All right. So if we think about it, if I add more of B, and Le Chatelier's principle says that the system will always try to undo or relieve whatever stress we do to it, well, if adding more of B is the stress, then it hopefully makes sense to you that the reaction system would try to use it up to get rid of it. So if we add more, the reaction system will shift in the direction that relieves that stress, which would mean taking away B. So which direction, forward or reverse, would use up B? Right? So hopefully you would say the forward direction, because B is a reactant of the forward direction, right? So increasing concentration of B speeds up the forward reaction, producing more products, or in this case C, I'll just say both here, and using up the other reactant. So if we look at the graph, what's happening? Well, B went way up because we artificially sort of added more B to the container, right? And then we said that would speed the forward reaction. And so if the forward reaction speeds up, immediately after this stress, you see the concentration of C, which was at equilibrium or was constant, C starts to shoot up because we've sped up the forward reaction, right? You also see A, which we didn't add any A, you see it start to go down along with B, right? Because the forward reaction is speeding up, and that would use up both of them, all right? Now, eventually, we're going to reestablish equilibrium, and you can see these lines kind of flattening out here, okay? We're going to reestablish equilibrium, and even though the concentrations won't be the same as they were back here, so we had equilibrium before with whatever these concentrations are, and they're not the same concentrations, but the ratio, or I shouldn't say the ratio, but the KEQ value, products over reactants, would give you the same answer. Okay, and if we think about this, that would be because while I increased B, I decreased A, which is the other reactant, right? And I increased C. Now, before we get any further, let's talk about why did equilibrium get reestablished? Well, if I stress it by adding more B, and that pushes the reaction forward to produce more C, well, eventually, now I've got more C, it's going to start going, the reverse reaction is going to speed up. And so they just sort of eventually balance out, and they're both happening at the same rate, and we've reestablished equilibrium. But I've increased B, I've increased C, and I've decreased A. So the KEQ, which, we could write the KEQ expression for this, is not changed. The actual values that the concentrations down here at, after time equals, or time 4, are not the same as they were between time 2 and time 3, right? Those values aren't the same, but the KEQ answer, if you plugged them into the KEQ expression, would be the same as it was before. So KEQ is not changed once equilibrium is reestablished, and this is because while B increased, A decreased, and it's the other reactant, and C increased. In other words, if I look at the KEQ for this, the KEQ expression for this would be concentration of C squared over concentration of A times concentration of B, right? And I'm saying squared because of the coefficient here. Well, yes, B went up, which if that happened in a vacuum, by itself, that would change my KEQ. But at the same time, C went up and A went down. So there's sort of a leveling off, and the KEQ stays the same. One way to look at this is using this little seesaw. This is a good memory device a lot of students like to use. So anything you add to the product side makes, if you've ever seen a seesaw before on the playground, this is the reactant side, this is the product side. Anything you add to the product side is going to weigh down the right side of the equation. And so the reaction will go back to the left to try to create more reactants and even out that balance of that seesaw. So anything you add to the right will cause the reaction to shift to the left, and anything you add to the left, like we did in this case, will cause the reaction to shift to the right. So it's always moving towards balance. Okay, another one would be change in pressure. So pressure changes only affect the equilibrium system if we have unequal moles of gas on either side of the equation. And I think a word or two got cut off there, but that's what we're saying there, on either side of the equation. So if you look at this reaction, we have 4 total moles of gas on the left, and of course just 2 moles on the right. So we have an unequal number of moles of gas. Well, creating more gas would create more pressure, right? So in this case, shifting, if the reaction system were to shift to the left, that's going to increase the pressure. If it shifts to the right, where we're only making 2 moles, that's going to decrease the pressure, right? So in this case, adding pressure would shift the reaction to the right. So if we add more pressure to the system, maybe by squeezing the container, making it smaller, doing something like that, adding pressure results in the system shifting to make less gas would relieve that stress. Okay? And you can do this by changing volume. Usually that's the most common way that pressure is changed in the system. Okay? So if we added pressure to this system, it's going to shift to the right because there's only 2 moles of gas on the right, which represents a decrease in pressure. All right? If we expand the container and we decrease the pressure, that would shift in the direction of more moles of gas, which would be to the left. In this case, the KEQ isn't changed either, because as soon as I change that pressure, right, a couple seconds later, the reaction shifts to make up for that stress. So for example, if I increase the pressure and it shifts to the right, well, now I've got a higher concentration of my stuff on the right. So now the reaction is just going to shift back to the left. Okay, so the KEQ value is not changed because after relieving the stress of a pressure change, the reaction shifts to relieve the stress of concentration change. So in other words, you just made more NH3, so now the reaction has to shift to use some of that up. Okay, the last stress is change in temperature. So heat can be considered a substance for the purposes of Le Chatelier's principle. And if heat is, if it's an exothermic reaction, you have heat on the right side, then adding heat, just like adding a concentration of a substance, would mean the reaction would want to use that heat up. Okay? So adding heat is going to be like adding a substance, in this case, to the right side of the equation. So this is going to cause a reaction to try to use that heat up. Shifts in endothermic direction because heat needs to be used up. Okay, so if I add heat to this reaction, it's going to shift to the left to use up that heat that I added, right? If I cooled it down, I put it in an ice bath, it's going to shift to the right to generate more heat, to release more heat and bring that temperature back up. So this time, though, the KEQ is changed. And we've already said that KEQ is temperature dependent. And it's for this reason, because every reaction, whether we list it or not, has heat somewhere. It's either on the right side or the left side, and it's either a little or a lot. But regardless, there will always be an effect of changing temperature on the equilibrium system. And the reason that I always think of this is because when you're raising the temperature, you're putting something in a cold water bath or a hot plate, it's like a constant stress. You're constantly adding heat. And so the reaction has to take up a new equilibrium where it's favoring either the endothermic or exothermic direction. And so for KEQs, we usually see a temperature listed with it because it is specific to that temperature.